Lab 5 Faraday's Law with Tamura. Introduction. We use Faraday's Law to relate magnetic field of a falling bar magnet to an induced current in an aluminum tube. We create a computational model that mimics this lab. Some physics principles that we use in this lab are Newton's second law, Faraday's law, and Lenz's law. The procedure. First, we drop a bar magnet through an aluminum tube. Then we record the time it takes for this bar magnet to fall through the tube. We repeat this 5 times, and we measure the average fall time. The measurements I got were the tube length, which were 0.3 meters, and the tube radius, 2 centimeters. The table on the right shows the time of the 5 trials, and the average time it took for my experiment was 1.33 seconds. For the computational model, I approached it with 4 ways. First, I created the aluminum tube and the bar magnet in the code. Secondly, I created a function to calculate the magnetic field of a bar magnet. Thirdly, created a function to calculate the flux dt. And lastly, the simulation code to show all of this, which is given. Here you can see the section of the magnetic dipole calculation function, and then below that you can see the function to calculate the flux dt. After running the code, it will show the magnet falling through the aluminum tube as seen on the image above. And then it will also output a graph of velocity versus time. It is interesting because you can see that the velocity reaches to a constant level. Interpreting the simulation. The blue ring represents counterclockwise current and the red ring represents the clockwise current. When the magnet was flipped, the current flows in the opposite direction. And the total time in the tube for real world was less than the computational one, and this difference could be due to error from Lab 3 because we calculated the magnetic dipole moment in Lab 3. Since the velocity reaches a constant state, net force acting on a bar magnet becomes 0. The results and source of error. So the time for observed, which is the experiment, was 1.33 seconds. And the time for the magnet to fall through the tube in the computational model was 1.56 seconds. This model percent error, which is just the difference percent error, was 17% for me. Some sources of error are air resistance, human error in measuring time, and smaller dy in the computational model would mean that there will be much more accurate results. And the dipole moment in Lab 3 could be wrong. Conclusions and questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So the falling magnet will be slower because there will be a greater current and a force upward. Second question, what if holes or slots were cut into the tube? How would this affect the ring current in your model? If the holes are cut, that would mean that there will be less magnetic force upward and the magnet will fall faster. That's it. Thank you.